matter can exist in the form of elements, compounds, and mixtures. When elements were discovered, a proper classification was required for their easier and better understanding. Many scientists adopted different ways to classify them. They tried to find out some pattern or regularity in the properties of elements. The first among them was Johann Wolfgang Döbereiner, a German scientist who in 1829 found some groups of 3 elements which showed similar properties. These groups are called as Döbereiner triads. Here, if we have a look at triad table, we can see that the atomic mass of the middle element is approximately the mean of the atomic masses of the other 2 elements. As this classification was a primitive step, Döbereiner could identify only some triads from the elements known. Other triads did not obey the rule. Hence, the system of triads was not useful. After the failure of Döbereiner's triads, the next attempt to classify elements was done by British chemist Newlands. By this time, 56 elements were discovered. He arranged all these elements in an increasing order of their atomic masses and found that every 8th element had properties similar to that of the first. He compared this to the octaves found in music, and therefore this classification was known as Newlands Octaves. However, this classification had its own share of shortcomings, the main points being that Newland could arrange elements only up to calcium out of the total 56 elements known, after which the elements did not show similar properties. Also later, several new elements which did not feature in Newland's classification were discovered. After the failure of Newlands Octaves, Dmitry Ivanovich Mendeleev, a Russian chemist, put forward a periodic table that was called Mendeleev periodic table. Mendeleev examined the relationship between the atomic masses of the elements and their physical and chemical properties. He believed that atomic mass of element was the most fundamental property in classifying the elements. He arranged the known elements in the increasing order of their atomic masses and their properties, and thus created the first periodic table containing 63 elements, till then known as Mendeleev's periodic table. Mendeleev's law states that the physical and chemical properties of elements are a periodic function of their atomic masses. In the Mendeleev's periodic table, the horizontal rows in the periodic table are called periods. There are in total 7 periods. The vertical columns in the periodic table are called groups. There are 8 groups, numbered from 1 to 8. Mendeleev kept some blank spaces in this periodic table. The vacant spaces were for elements that were yet to be discovered. He named them Eka boron, Eka aluminium, and Eka silicon, and also predicted their properties, which later were found to be correct. When noble gases were discovered, they were placed in Mendeleev's table without disturbing the position of other elements. The Mendeleev's periodic table, however, had its own demerits. Firstly, no fixed position could be given to hydrogen in the table, as it resembled alkali metals as well as halogens. At certain places, an element of higher atomic mass has been placed before an element of lower mass. For example, cobalt, whose atomic mass is 58.93, is placed before nickel, whose atomic mass is 58.71. Also, some elements placed in the same subgroup had different properties. Example, manganese, Mn, is placed with halogens which totally differ in properties. Due to these irregularities, a need for a new classification thus emerged. In 1913, Henry Moseley, an English physicist, discovered that atomic number is the most fundamental property of an element and not its atomic mass. This discovery changed the whole perspective of elements and their properties. Accordingly, Mendeleev's periodic law was modified into modern periodic law, which states that the chemical and physical properties of elements are a periodic function of their atomic number. The periodic table based on modern periodic law is called Modern Periodic Table. Many versions of this periodic table are in use, but the one which is most commonly used is long form of Modern Periodic Table. We shall now learn in detail about the Modern Periodic Table.
Chemist and inventor, and back in the mid-19th century, he devised the periodic table, which organized all of the known elements. In fact, when he made it, it even predicted new elements that we hadn't discovered yet. As we saw in our video on elements, everything in the universe is created from different combinations of the elements in this table. Just like a book, it's read from left to right and from top to bottom, with the elements arranged in order of increasing atomic number, which represents the number of protons in the atoms of that element. Within each of these boxes is the nuclear symbol for that element, which has three components. On the right, we have the elemental symbol, which is the one or two letter symbol for that element, in this case Na, which stands for sodium. In the bottom left, we have the atomic number, which tells us how many protons the atoms of that element have. And in the top left, we have the mass number, which tells us the total number of protons and neutrons in that atom. While he was organizing the table, Mendeleev found that the elements displayed a pattern of chemical properties that repeated at regular intervals. So instead of arranging the elements in one long line, he formed a new row every time the pattern repeated, which we now call periods. Because the patterns repeat with each new period, the elements in each vertical column have similar chemical properties, and we call each of these columns a group, starting with 1 on the far left and going to 7. So here we're looking at group 2. There are a couple of exceptions to this though. One is that the far right group is called group 0 rather than group 8, and we'll take a closer look at why this is in a minute. The other is that the block of metals between group 2 and 3 don't have group numbers. Don't worry about this for now though, just remember to ignore them when counting your groups. The reason that elements in each group have similar chemical properties is that they have the same number of electrons in their outermost shell. And this is largely what determines how an element reacts. In fact, the group number actually tells you exactly how many electrons they have in their outer shell. So as we're looking at group 2, we know that every element in this group has 2 electrons in its outermost shell. Just make sure you don't get confused here. All of the elements in a given group have different total numbers of electrons. They just have the same number of electrons in their outermost shell. So if we move over to the group 1 elements, which we call alkali metals, we can tell that they all have 1 electron in the outer shell, whether it's lithium, which has 3 electrons overall, or sodium, which has 11 electrons overall. And it's this feature that gives all group 1 elements similar properties. For example, they all react violently with water. There are also trends within groups. For example, the group 1 elements become more reactive as you go down the group, as we'll see later in a video specifically on group 1 elements. Group 7 elements, meanwhile, which we call halogens, all have 7 electrons in their outer shell. although these elements become less reactive as you go down the group. As we said before, group 0 is a bit different. These elements are called the noble gases, and they all have full outer shells. So argon, which has 3 shells, has 8 out of 8 in its outer shell, while helium, which only has 1 shell, has 2 out of 2. Because if you remember, the first shell can only hold up to 2 electrons. Because they don't need to gain or lose any electrons, the noble gases are all very unreactive. Sometimes you might see a zigzag line running here, from aluminium to polonium. This line separates the metals, which include everything to the left in orange, from the non-metals on the right, still in blue. So as you can see, there are lots more metals than there are non-metals. And in the middle of the metals, there's a special block of elements, which are known as transition metals. We'll take a closer look at what these are in another video, just like we'll take a closer look at the group 1, group 7 and group 0 elements, and the differences between metals and non-metals. Before we finish, we just wanted to point out that if you Google periodic table, you'll probably see loads of different types. For example, you might find that the position of the mass and atomic numbers has been reversed, like the example of iron here. Don't worry about any of this though, the tables all show the same information, just presented in a slightly different way. And you can always tell which is the atomic number, because it will be the smaller of the two. And in your exam, the periodic table you'll get given will be similar to the one we've been using throughout the video. That's it. 1 elements, which are known as alkali metals, are a bit different from most other metals. They include lithium, sodium, potassium, rubidium, cesium, and francium. Instead of being strong, having a high density, and having a high melting point, like you expect of a metal, the alkali metals are in fact relatively soft, with low densities and low melting points. They are also much more reactive than other metals, and react vigorously with water, oxygen, and group 7 elements such as chlorine, as we'll see later. As you go down the group, the elements become even more reactive, with cesium being so reactive that it can ignite spontaneously at room temperature. Another trend as you go down the group is that the melting points and the boiling points decrease. Now, an easy way to remember this trend in reactivity is that common table salt, which has sodium in it, doesn't just suddenly catch fire as you sprinkle it on your potatoes, whereas cesium probably would. Now, a big part of chemistry is explaining the properties and trends that we see. For example, how would you explain the fact that alkali metals are so reactive? Well, if you remember from our electron arrangement video, which we'll link down below, all atoms want to have a completely full outermost shell in order to be stable. And because the alkali metals are all in group 1, we know that they all have 1 electron in the outermost shell. So in order to react and be stable, all they need to do is lose that 1 single electron, which is pretty easy because there's only 1 electron to lose. And because they lose a 1 negative charge, they'll become a 1 positive ion. What about the trend that we mentioned though? That they become more reactive as you go down the group. Well, as you go down the group, the atom's radius gets bigger, and so the outermost shell gets further and further away from that positive nucleus. Now, as this positive nucleus is the only thing holding the outermost electron in place, the increased distance weakens the attractive force between our positive nucleus and that outer negative electron, meaning that the electron can be lost more easily, increasing the atom's reactivity. Remember, the term reactivity isn't anything special. It's just related to how easily atoms can lose or gain electrons, and so react with other atoms. Because alkali metals can lose their outer electrons so easily, they almost always form ionic compounds with non-metals. We'll take a closer look at ionic compounds in another video, but it's basically where a metal atom, like sodium, donates an electron to a non-metal like chlorine, so that both of them have full outer shells. And because these two atoms are now oppositely charged ions, they'll be attracted to each other by electrostatic forces, which we call an ionic bond. And so together they make an ionic compound. This particular example of sodium chloride actually happens to be common table salt. But regardless of the alkali metal used, the ionic compounds are generally white solids, and they tend to dissolve in water to form colourless solutions. So now that we've covered alkali metals in general, we need to consider how they react with water, chlorine, and oxygen. When an alkali metal is put in water, it reacts vigorously to produce a metal hydroxide and hydrogen gas. For example, sodium plus water will form sodium hydroxide plus hydrogen. As we mentioned earlier, the metals become more reactive as we go down the group, and so the reactions will release more energy. In fact, from potassium onwards, so much energy is released that it ignites the hydrogen gas that gets produced, which we can see in the form of flames. Group 1 metals also react vigorously when heated in chlorine gas, and in this case, they form white metal chloride salts. So sodium plus chlorine would form sodium chloride. And again, the reactions will become more vigorous as you go down the group. When alkali metals react with oxygen, they form metal oxides. However, the type of oxide they form will depend on the particular metal. For example, lithium plus oxygen forms lithium oxide, Li2O. Just like sodium plus oxygen forms sodium oxide, Na2O. However, sodium and oxygen can also react to form sodium peroxide instead, which is Na2O2. Meanwhile, potassium can react with oxygen to form either potassium peroxide, K2O2, or potassium superoxide, which is KO2. Now that's quite a lot to remember, and you don't really need to know why these particular compounds form. So the best trick is probably to just put them on some flashcards and practice them whenever you need to know them for exams.
Earth metals. The alkaline earth metals are found in group 2 of the periodic table. They include beryllium, magnesium, calcium, strontium, beryllium, and radium. The alkaline earth metals share several common properties. They have low density, they are silver and soft metals, they are ductile and malleable, they react with halogens and water. Alkaline earth metals are reactive, but not quite as reactive as alkali metals. This is because they all contain 2 electrons in their outer shell. Because they are reactive, they are usually found in nature in compound form. Here are some common uses for the alkaline earth metals. Strontium compounds are often added to firework displays for their red flame test color. Calcium is used by our body for our teeth and bones. Magnesium is used in antacid, and beryllium is used in light bulbs. So there we go. Group 2 alkaline earth metals. They each have 2 valence electrons and share other properties.
7 elements, known as halogens, and the group 0 elements, known as the noble gases. And we'll run through the properties and the trends of each of them. Let's start with the halogens, which are all in some way pretty dangerous. Fluorine is a poisonous yellow gas and is very reactive. Chlorine is less reactive, and this time a poisonous green gas. Bromine is a reddy-brown volatile liquid, and poisonous again. And iodine is a dark grey solid that can form poisonous purple vapours. Although iodine is also an antiseptic, which has saved millions of lives. And for those last 2 elements, astatine and tennessine, you can basically ignore them, because they don't really come up in the course. All of the halogens can exist as pairs of atoms that we call diatomic molecules, which just means 2-atom molecules. They do this by sharing electrons and forming a covalent bond, as we've shown here for chlorine. Although this outer shell arrangement would be the same for any of the halogens. Halogens can also form covalent bonds with other nonmetals, such as hydrogen or carbon, to form compounds like hydrogen fluoride or carbon tetrachloride. These compounds are known as simple molecular structures, and we take a closer look at them and the covalent bonds that they use in another video. Just like the group 1 elements, group 7 also has trends as you go down the group, but they're the opposite way around. So for halogens, the melting points and boiling points increase as you go down the group, and the reactivity decreases. This decrease in reactivity is because as you go down the group, the outermost shell gets further and further away from the positive nucleus. So the attractive force that's needed to pull in an extra electron from another atom gets weaker. And if the halogen can't attract an electron to complete its outer shell, then it can't react. So the larger atoms at the bottom of the table, like iodine, are the least reactive. The next thing we need to look at is how halogens form ionic bonds with metals. When a halogen gains an electron to form a 1- ion, we call it a halide. And we have to change the name slightly, changing the N's to D's. So we get fluoride, chloride, bromide, and iodide, all of which would be ions. You'll probably most often see halogens forming ionic compounds with the alkali metals in group 1, like sodium chloride as we have here, but they can form ionic bonds with metals of other groups too. Lastly, we need to take a look at displacement reactions. These involve a more reactive halogen displacing a less reactive one. For example, let's imagine that we pumped some chlorine gas into a solution of potassium bromide. As the chlorine is more reactive than the bromine, because it's higher up in the group, it displaces the bromide to bond to the potassium. So effectively, the chlorine has taken the bromine's place to form potassium chloride. The main thing to remember here is just that more reactive halogens will always displace less reactive ones. For example, fluorine, chlorine, and bromine could all displace iodine, as iodine is the least reactive. Now, we were going to do an entire video on the group 0 elements, which are also known as the noble gases, but there really isn't that much that you need to know. They all exist as colourless gases, and because they have full outer shells, they're inert, which just means that they don't really react with anything. And because they don't react with other atoms, they exist as single atoms, and they're also non-flammable, which means they can't be set on fire. The only other thing that you really need to know is that their boiling point increases as you go down the group, just like it does for the halogens. Lastly, we have the transition metals, found in the center of the periodic table, here in green. You can think of these as being typical metals, as they have all the metal properties we mentioned before. They also have some extra properties though. One of these is that transition metals can form more than one ion. For example, chromium can form 2+, 3+, and 6+ ions. And these transition metal ions are often coloured. For example, the aqueous forms of these ones would be blue, green, and orange. The most important practical feature of transition metals, though, is that they make very good catalysts, which is an important term to remember. We can describe a catalyst as substances which increase the rate of a chemical reaction without being used up themselves. For example, you'll see later in the course that iron is an important catalyst in the Haber process, which we use to make ammonia, while nickel is used in the hydrogenation of alkenes, which we use to make margarine.